All right, let's wrap up the artificial intelligence slides, shall we? So, yeah, let's keep on trucking and we're learning what it means to be artificial intelligence. Like, how do you learn things? We talked about a few ways. We found some cool websites that did fun stuff, and then we ended talking about like playing games. Computers can play against themselves, and then slowly but surely learn those neural virtual pathways uh, to get things working. So yeah, let's talk about other applications of artificial intelligence. So a very important one, hopefully one day it'll work well enough, is self-driving cars, right? So what is that? But like you have some sort of camera, and you got that on the screen, and like it's just drawing boxes all day. It's just blink detection from those digital cameras all over again, is it not? So what do you have to do if you're a self-driving car? You have all your sensors, you have your camera, maybe even infrared stuff, but you just need to figure out like you got to draw boxes around things. Right? Where's the road? Which side can I be on? Where are all the pedestrians? So like here's an example of like what you would have to do if you were the sensor in a self-driving car. You'd have to notice like, oh, this is the side of the road that I need to be on. Right? I'm not allowed to be over here. That's the dividing line. That's not okay. You have to notice the other cars so that you don't run into them. If they accidentally swerve at you, you got to fix that somehow. You got to notice any pedestrians crossing the street. Even if you have a green light, you can't go, right? While they're still crossing. You got to notice where the lights are, what you're allowed to do, all the lane markings as well. Like you got to be in the left turn lane if you need to make a left turn. All that stuff. You need to essentially draw a bunch of boxes, right? And so, how do you learn that? Somebody needs to give you a bunch of training data, a bunch of pictures with the boxes drawn already, and it's your job to figure out why. Okay, figure out where all those things are, all those pieces are, and then once that is all figured out, right? That's only the first step. That's like noticing your surroundings. Then you have to act based on those surroundings, right? So it's even extra training data. Given this, what did the human driver do, right? How should you be responding to these things? It has to go out and use this data to control the wheel, the brakes, the accelerator, all that stuff that you use on a car, the blinker, right? All that fun stuff. So that's pretty interesting. And so it's a hard problem to solve. That's why it's not been solved completely yet. They still are testing in like San Francisco and in the desert, right? But one thing that I read that sounds kind of fun and promising that hopefully we'll get at one day is that like in the future it won't make sense to own our own cars because like you could just rent one for the journey you needed to make. It would just drive itself to you and take you there. So it's just like a giant fleet of self-driving cars might be the future one day. That's kind of fun to think about. All right, but we're not there yet. So here's a fun example from a couple years ago where like we're at the level where you can still trick cars. Like a Tesla, some hackers ended up tricking a Tesla into thinking that the speed limit was 85 miles an hour, even though it was 35. But they just put a little piece of tape right there to make the three look and stick out a little bit more. So that is very unfortunate, right? That's something that that's a mistake the human would never make, right? You'd be like, no, there are houses. I'm not going to go 85 right now. But the Tesla was like, all right, 85 it is. So that's something that still needs to be solved, right? So we're going to get there eventually. So that's fun. Another thing I want to talk about, I think we've brought it up in a few different ways, but like the internet, it's a horrible place, right? So people say bad things, and we'd like to filter that kind of stuff out. We should allow that to be posted a lot of the time. So like on Twitter or X or TikTok comments, whatever, wherever you're looking, no human is going to look at all those things. Nobody's going to look at every comment on Reddit, right? There are a bunch of tweets a second. There are a bunch of comments a second on YouTube, for example. How do you keep things nice enough, right? How do you keep it a safe space? So one solution that people employ is to use what's called natural language processing. I've said that word a few times, right? That's just like figuring out what something is trying to mean, trying to derive meaning from text. That's analyzing your words. A special subfield of natural language processing is called sentiment analysis, where you take the text somebody's typing, like their tweet, is like, oh, that's a happy tweet. That's nice. This is a sad tweet. Like, I'll keep that. And then maybe like if you notice that it's an angry tweet, you should probably maybe hand that off to a human, make sure they're not like doing anything bad. They're not saying anything wrong. So yeah, that allows you to discover the tone of some writing. That's a topic of current research right now. people are trying to figure out like, well, how happy is this writing? Is it subtly happy, subtly sad, subtly angry? Because those might need to be looked at by somebody to make sure that they're safe for the social network that we're on right now. Okay? So yeah, just a bunch of little ideas. Any questions about this so far? Comments? Hopefully we've heard a little bit, but we're just hitting it harder. Alright, here's a fun thing I want to tell you about. I have some weird, silly things to tell you about before we end the artificial intelligence slides. So, first thing is called the Turing test. Have any of us heard of the Turing test before? It's a fun idea, and I think it's probably solved these days now, thanks to ChatGPT and stuff. But here's the Turing test. This used to be like the holy grail of artificial intelligence. If you could make a program that passes the Turing test, you are set, right? And I think we've done it by now. I think it's at our fingertips, which is very fun. This used to be just like a pie in the sky dream. So the Turing test is this. It's like a game, and let's say that you're person C, right? So you're going to take part in the Turing test. And so somebody, a researcher, they take you into a room. Nobody else is in that room. They give you a computer. They give you a computer that you can type into. Maybe it's like connected to Discord or like some sort of chat room somehow. And the idea is in two separate rooms, there's one human in this chat room that's interacting with you that you can type to, and then there's also a computer pretending to be a human, okay? And so you can talk to them. Don't know, the experiment doesn't, like, there's no set time, like it could be a long time, could be a short time, but you end up asking questions through your text-based means, right, through the computer, to each of these two entities, and it's your job at the end of your time limit to guess, or like say with, I guess, conviction, which username in the chat room was the computer, and which do you think was the human? Okay, so that's the Turing test, and the computer passed the test if you were unable to tell. Right? If you were unable to tell, the computer passed the Turing test. We say they were able to convince you, like it was like with enough experiments that like it was just like it came down to random chance whether or not the computer was you guessed it properly. It's like a 50-50. If that happened, the computer passed the Turing test. And honestly, depending on the length of that test, maybe if you ask if you're talking to the human and the computer for hours, you can finally figure something out. But for a short while, asking questions to ChatGPT, for example, computers can do pretty good, which is nice. So like chatbots on websites trying to help you with things like automated stuff can usually get at what you're trying to ask for. I remember that I called when I bought this laptop from Apple. I called them once while they were trying to send it to me because I did something wrong, and like it was just a completely automated system, and I had to say like no. Like they had most of the issues there that they knew about, but I had to say no, I wanted something different, and then they finally gave me a human. They're able to do pretty well these days. That's fun to think about. So you've probably interacted with a lot of computers by now, and maybe they passed the Turing test. Cool. So yeah, that leads us to like the GPT models, which like I had this slide way before ChatGPT came out, back when it was GPT-3, GPT-2, but like here's an example article. Like it's not very surprising anymore, but like this is an article that's written by AI. Okay. Look, I'll just give you a couple seconds to read it. It was more mind-blowing 4 years ago when I first started teaching here. But this is the kind of thing, if you've never used ChatGPT, like this is what it can do. Like it can create like knowledge. It can lie about stuff. Like this is supposed to be a news story. It's not true, right? Which is very interesting. So it's very, very good. And it's getting better every day. So like it was made by a computer, of course, which is awesome. And yeah, it was just given that short prompt. It was like, write an article about this thing, and then it filled in the rest. Okay. And this was from this article, this thing that it made up. I think it was either from GPT. I think it was GPT-3. Back before that was available for people to use on ChatGPT. I think it was either 3 or 2. But yeah, this was a neural network, right? It was a bunch of virtual neurons talking to each other, and it was great. right? It was doing everything. It was creating speech, or creating text at least, and it was thinking about what the next word should be. I'm sure you've hopefully read a little bit about ChatGPT these days, or seen a video about it. But yeah, all you do is you give it text, and it like completes the text. All right. So that's the cool thing about it. It's just like somehow sending numbers around a giant neural network just allows you to eventually output the right text to follow what you're doing, which is really cool. Right? So like, for example, you should never do this, right? Like for your English classes or for our essays, like you could probably ask it to write an essay for you, and like I would be none the wiser. So please don't do that. But yeah, let's experiment with that. If you've never used ChatGPT before, let's try it together. So there's this place that lets you use ChatGPT without an account. Let's see if it still works. If you go to this website, is it still here? Cool. So you can use ChatGPT. You can also use some of Facebook's stuff. Like you can change these, but there's GPT 3.5. But yeah, play around with it. It's sdk.vercel.ai/prompt. You go there and just like take a couple minutes to like ask it things. But while you're loading it and trying it, let's have it write something. Let's have it write an old essay just to get it out of our system so that you never actually do it in class. It's like write a 750 or 500 word essay about what was it? Therac 25. Therac 25 machine. Its issues and what you would do differently to prevent that tragedy. Something like that. I don't know. And then you'd be like, run playground. And then it writes an essay for you, and please never actually do this. But it's very, very convincing. It's like, one of the major issues was with its user interface design, because it was not telling people when problems were there, right? The software had a bunch of bugs that could cause malfunctions, and so like it's very cool, and you can see like the difference between all these other things. But you can ask it to like make a joke for you, or like tell you why computer science is a good field to study. But do whatever you want. Play around with it for a couple minutes. Feel free to have it write an essay for you, just so that you don't actually do that in the real class. But it's fun. It's so powerful. It's just a bunch of virtual neurons talking to each other, sending numbers across, and those numbers eventually tell it which words to pick. Well, it's trying to do. It was trained on the entirety of like Wikipedia, the entirety of the internet. And remember what it's and trying to use previous text to predict the next text. That's all it's been trained on. Magic. Oh, that's my timer. Were you able to generate something convincing? What did it say? Oh, are you kidding me? Oh, it's probably tied to our IP address. I'm sorry, so I ruined it by doing it first. That's hilarious. So if you have a VPN, then you can log in here. Or maybe you have to make an account or something. I'm sorry. That's my bad. But there are other websites. You could have tried these, I guess. These ones also work. That's so dumb. So if I refresh it, I've used my free token. No. I don't know. Actually, I'm on the Wi-Fi, so it should be one of you got it working, and then the rest. That's too bad. But yeah, if you want to make an account, or you just like make a ChatGPT account, it's fun to play around with. Right? So I highly encourage you to experiment with it. It's useful. It's useful for non-cheating ways, right? It can help you study for things. It can give you a study guide for one of your classes if you give it some topics. You can have it come up with example questions for you. It's really, really cool. But yeah, you can go here at home at least, and then you'll get your free tokens or something, or you just make an account. So yeah, that's what I want to say about that. Any other questions, comments? All right, let's next. The last thing I want to talk about is the weirdest thing. It's called the singularity. So have any of us heard of it? It's like a horror story of like what could happen if AI went bad, if it went rogue. So this stems from the idea of us training computers using themselves, right? So like when we made the AIs to play the chess game or the Go game, they were able to like get better by playing against each other, by playing against themselves. And so like it'll get better every time without any extra human input. All it needed was the rules of the game, right? And that's very powerful because they're essentially thinking on their own. They're getting better. They're learning things and strategies that the human maybe has never seen before, that's never invented. So that's kind of cool to think about. And so you can take that question and ask it about like just AI, like a ChatGPT style thing. Like what if the same thing happened for general machine intelligence? Like you could make a computer that could think in a way and like learn by itself and get better, and eventually like it could reason at the level of a human. Yeah, that's the goal. All right. So what if we could do that? One day maybe we'll have that kind of computational power and we'll have a good enough model. It'll all work out. But let's say, right, we have that thing learn. Like it got to the level of a human and then it learned a little bit more by itself. Imagine that we made the first computer that had a little bit more general intelligence than a human had. Yeah. Right now, computers are just like dumb but fast. Just imagine that they had the brain power of a human and then a little bit better. We could then copy that thing, right? We could copy whatever that machine learning model was and then have a bunch of smarter than human things existing and being able to reason for us. That's pretty cool. And then, because it's smarter than us, we could ask it to invent a better version of itself, right? Because it's smarter than us, maybe it would invent a version of itself that a human would never be able to come up with, right? And then it gives us the blueprints for that. We go off and we build it for that thing. And we just keep on copying that, having it think hard about how to make a smarter version of itself and learning more and more and more. And so, like, that process just keeps repeating, right? You can imagine that would keep repeating as long as we had processing power. That would lead to some sort of super intelligence, right? A computer that knows everything, that's much better than humans. And that's called the singularity at that point, all right? The second we made a computer that's smarter than humans, it can get smarter and smarter and smarter by itself, at least if we build those smarter things for it. So that's pretty interesting. That's called the singularity, and it's either a good thing or a bad thing, depending on whether or not the super intelligent computer likes us. So this is a fun quote that kind of gives you the perspective. It's like, the first ultra-intelligent machine is the last invention that man need ever make, provided that the machine is docile enough to tell us how to keep it under control, right? It's like, just that thing, just if we make that, we can tell it, we can ask it to like, build a better version of this machine for us, build a better version of this machine for us, and it'll figure it out because it's smarter than humans. So that's pretty cool. So then computers run the world, and maybe hopefully they keep us alive. So that's called the singularity. When the computer gets smarter than a human, we can just like set off a chain reaction, which is really cool to think about. Any questions about that? Any ideas? Maybe we've read some science fiction with that in mind. That's an interesting thought, at least. So yeah, if we're good with that, let's switch gears to a different topic. We're in between slides again. So the next thing that I want to talk about is called qualifiers and quantifiers. It's more logic. So we're going back to more logic-y kind of stuff. So let's start with qualifiers, because that's more informal kind of logic. Just stuff that you use in your day-to-day life. So qualifier. You qualify your statements, right? Because when you say something, especially when you're arguing, like nothing is absolute. You're not saying something like this is always true, right? You're never usually saying that unless you're thinking about what Kant might say. So when you're trying to argue, for example, or when you're trying to just say something correctly, like you need to oftentimes soften those statements that you're making, so that like it's just not like a bunch of generalizations that are not really true. Yeah. So here's just an example of a qualifier, right? I could say this. This is a true statement, right? Almost every day in Fresno in July is unbearably hot. Yeah, it's more or less a true statement. Somebody might be able to like respond and be like, no, there's that one day where it was in the 80s, it was kind of cloudy, it's all right. But then that's not a correct argument because I said the word almost, right? I said almost every day is unbearably hot in Fresno in July. Okay? That's a qualifier. That qualified my statement. So if I didn't have the word almost, then that would have been a good response. You see that? So we do that just naturally as humans, right? When we're trying to say stuff, like almost every day. Just trying to make sure that we're not saying something that isn't true. Almost every day, not exactly every day. Yeah? That's a qualifier. And so there's plenty of qualifiers, right, that you've used. Like there's like a whole spectrum of them. There's like everything is always, this thing is always true, this thing is never true, or this thing is true sometimes. There exists a case where it's true. Almost never is it true, but sometimes, generally, usually, this thing happens, right? Almost always this thing is true. You can see that there's a spectrum there. And that's what you got to use when you're trying to be precise. You're trying to, like, write an academic paper, for example. You're trying to get published with your research, things like that. So can you imagine in your head some ideas that involve qualifiers that maybe you've said recently or you've heard about in classes? I'm sure you can. Like one that I can think of, like if you go back to the pandemic, it's like people were talking about the effectiveness of vaccines, right? Like COVID vaccines are generally effective. That's a true statement, right? Back in the day. Generally effective. Because for certain people, like they were still going to get the virus with its full force, but the whole point of getting the vaccine was to like stave that off a little bit for most people, right? So they're generally effective. And so maybe that has to go with like an 80% chance of you getting a lesser form of the virus or something. That's like, that corresponds to the qualifiers of like mostly. It's mostly effective. It's generally effective. It's not always going to work, right? Just like any drug. Generally. But there's a good chance. And so that's why people were arguing that you should get it, right? So that is a qualifier. And I'm sure you've seen that definitely, like, watched a lot of Hulu commercials over the break. And so, like, for some reason, they advertise drugs. I don't know why that's legal, but they say stuff like that to cover their tracks, right? Generally, usually, everything's fine. So, okay. I hope that makes sense. So those are qualifiers. That's stuff used in, like, informal arguments when you're talking to people. Let's try to bring that back to computer science and like programming computers to reason about things. How do we do that? How do we like write logically exactly what we're saying so that everybody can understand it? That leads us to something called a quantifier, right? And so this is part of like hardcore logic stuff. So this is part of logic. And quantifiers are symbols. Just like our combinators for Boolean expressions, like our ands, our ors, our nots. Remember those symbols? it's a similar kind of thing. We're going back to that math stuff. So math time. Time for more stuff, more mathematical symbols to learn. Okay? Because we think in terms of qualified statements, we would like to translate those sentences that we're writing into a computer, or into math at least, so that you can prove them beyond a shadow of a doubt. That's our end goal. We want to think very logically, so that maybe we can make a program that's correct in terms of these qualifiers, right? We're going to turn them into quantifiers. Right, that's where we're going. And so I'm going to teach you 2 quantifiers in this class. This is generally a bit of a more weird topic, so definitely ask questions, pay a little bit extra attention. It's a weirder topic for the class, but it's a very powerful thing. Right, so here are the 2 kinds of quantifiers that I want to teach you. It's an upside down A and a backwards E. All right, it's just like you took those symbols, took an A and did a 180, and you also took an E, and you gave that a 180 as well. So that turns into those 2 things. So we can actually use just using these 2 in a combination of them, we can create most qualifiers logically, which is nice. If we also use like our ands, ors, and our nots together with these. Okay, so this 180 flipped around A stands for all. It's trying to make a statement that is, and say that it's always true for all cases. It's true. And then this flipped 180E is called there exists. It says that sometimes this thing is true. There is a case. There's at least one case where this thing is true, right? So there are some other kinds of quantifiers that talk about like time, like this thing's not true right now, but it'll be true later, or like in the future or the past and stuff like that. But those are that's like graduate level mathematics or computer science, and that is not what I'm trying to get at right now. But at least I could use the there exists in a sentence for you. But now those are quantifiers, and we can use them to express ideas that could then be proven or disproven. All right, so that's the step. It's like you can use it to write an idea that you can then prove true or false. Just like you can write a bunch of Boolean expressions with ands, ors, and not, like x and not y, and then you have to go and prove it true or false. You're not sure if it's true or false yet. All right, so you can use that to write bigger sentences about stuff. All right, so here's an example of, let's do for all first. So here's an example of the for all quantifier. We're trying to make the case that we have a variable, maybe it's in our program right now. We like to say that no matter what value our variable x has in our program, it's greater than 5. Right? And so this is how you would write that with our quantifiers. For all x is greater than 5. All right? X is always greater than 5. That's what it's saying. Right? Every value of x that it could possibly have, it's always bigger than 5. Does that make sense? So this is something that is not yet true or false. You have to go and prove it now, but it's an idea that you can then prove or disprove. So like if your program somehow had x being 2, like that's not allowed. It's not supposed to be that. So it's saying that x could be like 7 or anything bigger than 5. 6, 7, 8, 9, 10. That's what it's trying to say. When this is true, if this is a true statement, that means whatever x is, it's bigger than 5. Every value of x that it could take on is bigger than 5. For all x is greater than 5. That's how you say it. Okay? Does that make enough sense? It's a weirder idea. That's how you'd write that. Like I want to say whatever value this x has, for all any possible one, it's bigger than 5. For all x's, x is bigger than 5. Okay? Here's an example of there exists. That's the other one. So we can make a statement that we can then go and disprove. There exists a number n that is both prime and even. With quantifiers, you always have to include a variable. It creates a variable for you. And so here's how you translate this to math. There exists a number called n, and sometimes you put a comma and you'd be like, such that. There exists a number n such that n is both prime and even. And so n is prime. Imagine you could write that in math, and n is even. Both of those things are true. So that's using our other logical symbols. Does that make sense? This is saying, this is that translation. There exists a number n that is both prime and even. Does that make sense? How I'm reading that? And this is now a statement that you could then either prove or disprove. Is this a true statement? or a false statement, do you think? Is it true that there exists a number n that is both prime and even? Because this is just saying what you could prove. It's not giving you the answer yet. You have to go and prove or disprove it. Like if n was 7, that's prime, but it's not even, right? There is an even prime number, is there not? There's that one, just one. There's 2. 2 is the only even prime number. And so that means this statement is a true statement, because there is one number that could fill in for n. There exists at least one that could fill in for n that's both prime and even. Does that make sense to us? That's the secret there. It is a little weird of a concept, but that's the idea, right? And so, just getting in the habit of thinking in this kind of logical way, I want to give you a question, right? Let's go to the written ice page, if you can, humor me. And I'll stop attendance after that, after we finish, if I could remember at least. So please remember to do attendance if you've not yet done that. So let's go to the written ice page. I'll clear it out for us. Boop. Cool. And here's my question for you. Don't think about quantifiers just yet. It's not a big deal. I would like you to reason about sortedness, the idea of something being sorted. Right? Try to specify the property of sortedness in English. What does it mean if you have a list of numbers? What does it mean for that list of numbers to be sorted? Try to write it in as precise of English for now as you can. We'll try to translate that to math later, right? So like pretend like somebody has amnesia and you're trying to tell them what sorted means, or like it's a small child and they don't know, they've never heard the word sorted before. What does it mean for something to be sorted? Why is this list sorted? Right? What does it mean to ask that and say that L is sorted? Why? All right? So discuss as a group, see if you can come up with a good, as precise as possible English definition of sortedness, and we'll see if we can translate that to math using quantifiers, right? We got plenty of time. I'll give you a few minutes, and please help each other discuss. What does it mean for that list to be sorted? Maybe think about some examples of sorted lists. Try not to ask ChatGPT. Of course, I've lost my start menu. There you go. mean for something to be sorted? Simple words as possible. Yeah, that's my time. I take another 30 seconds to finish up typing your thought. Remember to press submit so that I can see it. And then let's see if we can figure it out. What makes that one sorted, not the others? Like, I mean, there are some synonyms you could use, I guess. But we'll have to talk about that. Alright, let's take a look. Yeah. Smallest to biggest, biggest to smallest, lightest to darkest. I like it, yeah. So if we're just talking about numbers, for example, yeah, something small to something big in that order. Okay, can we get more precise? Specific order that is consistent. I'm going to have to define what consistent means, probably, yeah? Group of numbers defined similar with one another, yeah. Nice. So, these are good thoughts. In order, yeah. So, order is important here. So, sorted is an order of things. It's a specific kind of order. So, like, what does that mean? Smaller to biggest, lowest to highest. Good. Putting into categories. I like that as well. So yeah, these are good definitions of sortedness. If we're just talking about numbers, it's probably like, for numbers to be sorted, like a list of numbers to be sorted, it means that things are in order, right? They're in ascending order. They're, I don't know, they're getting bigger. Yeah? Something like that. So thank you for that. I promised to stop that too, didn't I? So that's perfect. These are good options. Let's see if we can translate that idea to math. Just talking about numbers specifically. Let's zoom in on that idea. All right. So what does it mean that a list of numbers is sorted? So in English, it's like every element of this list, it's sorted because every element's like it's going and getting bigger, right? Something like that. Like a increasing line with positive slope. Every element is getting bigger. Yeah? Or wait, what if we had list L prime 1, 2, 2, 2, 3, 3, 4, 5. Is this still a sorted list? I have some duplicates. Is that fine? I think so, right? So I can't, this is not good enough yet. Every element's getting bigger. That's not a good enough English definition, right? Or, right, it's either getting bigger or staying the same. Does that make sense? Staying the same. Like, this is the kind of thing we got to think about if we want to mathematically specify what it means to be sorted. Staying the same. So that's a little weird. I wanted a quote, not a parenthesis. So, okay. So that kind of means, like, sure, this is sorted. This idea is sorted. That's like this list. But also, this is a sorted list as well. It's like staying the same or getting bigger. It's like a stair step. Yeah. So that both of those mean that it's sorted, right? And so, if we want to get as precise as possible, if we want to get mathy, what we're trying to do is we're trying to say, like, take all these elements of this list, arrange them. This is what's true about all of them. 8 is less than or equal to 27. 27 is less than or equal to 42. 42 is less than or equal to 79. 79 is less than or equal to 101. Does that make sense? That's how you define sorted in terms of like what it means to be in order, like a less than or equal to operation. That's probably as precise and as like low level of a definition as we can get. So how do we say this? How can we say this in math, in essence? As we're trying to get closer and closer to math. How do we talk about, like, yeah, these guys are related under, like, less than. These guys have a less than in common, too. These guys, less than, less than. One way to do that, and this is a little bit of an interesting jump, we could use indices, right? Because we have those in Python, at least. Just imagine we have some sequence of numbers. We can index them. 0, 1, 2, 3, 4 for this list, right? And what we're trying to claim is a lot of less than or equal to things at once about the indices. That's how we can hit everybody, right? We're trying to say, like, L of 0 is less than or equal to L of 1, because that would cover this idea, right? And then to get the next one, it's like L of 1 is less than or equal to L of 2. Yeah. And we want this to be true for every index of our list, such that like these make sense. Go all the way up to 4, yeah? So in general, like if we try to generalize this, just L at some arbitrary index I is less than or equal to L at some arbitrary index I plus 1, right? Like if I is 0, it turns into this one. You see that? If I is 0, this idea turns into this less than or equal to operation. If I is 1, it turns into this one. And we want this to be true for all I. You see that? That's what we want. We want this to hold for every possible I that it could possibly work for, such that we're not like getting too big on our indices, yeah? That's going to be the secret. That's how we're going to translate this to math, all right? This idea of something being sorted. This is what we can check. Check that every possible pair of elements that are right next to each other, because they're at index I and I plus 1, those are things right next to each other, checks that the less than holds for them. See that? That's how we can precisely specify. It's one way to do it in math that these things work out. So for every I that could possibly work for your indices of your list L, check and make sure that L of I is less than or equal to L of I plus 1. It's like you plug in I equals 0, that gives you this one. I equals 1 gives you that one. All the way up to I equals 3 gives you this one. And like that's your full list at that point. Does that make sense? That's pretty cool. And so if we go back to English, like how do we translate this math back to English? What it's saying is for every index I, like the side conditions, like every index I that actually works for L, it's not out of the bounds, we're trying to enforce the fact that L's element at index I should be less than or equal to L's element at index I plus 1. Okay? That's what this is trying to say. For every index I, this better be true. If this is true, then L is sorted. So this is a mathematical definition of a sorted list. You see that? It's very precise. It's very cool. And it's like just fill in these I's, have them work for every possible I that it's good for. And that's what it means to be a sorted list. Yeah? Does that make sense? So now I'm going to give you another similar question because we're going to try and do this some more. Like, all right, we went from English idea to mathematical precise definition. All right, let's do it again. So I have another question for you. Let's see. You don't have to write this on the written ice page this time. It's not a big deal. But in your head or with your partners, with the people sitting next to you, if possible, try to make a statement with quantifiers this time, if you can. Try to go from English to quantifiers. So these are your two quantifiers for all and there exists. And here's like the thing that we solved for last time. For all I, L of I is less than or equal to L of I plus 1. Let's say we have another list. All right? And we're trying to prove something about a list. What's a statement in math that would translate to this? We'd like to represent the idea that every non-empty list of numbers has a minimum. And that is a true statement. Something you could prove, but we just want to specify it precisely and formally. How can we specify that every non-empty list of numbers has a minimum element? And that's a true statement, right? It's like if the list is empty, then all bets are off. Don't include that. We're talking about non-empty lists. Every non-empty list has a minimum. Like a list of size 1, its only element is the minimum thing, right? If you have a list of multiple things, like 3, 1, 2, there's always something that's the smallest, right? Or if it's duplicated, like one of those, like they're all the same minimum, yeah? So every non-empty list of numbers, it really does have a minimum. How would you represent that with math, with quantifiers? Probably with some less thans, yeah? Some indices to pretend you have a list, call it L again, maybe. How would you say that? See if you can figure it out. Then I'll give you a 2-minute head start, let's say, and then I'll give you my thoughts and my answer. So what does minimum mean, by the way? Like, you have to figure out what that means too, don't you? It's like something about small. Something that's very small. Smaller than everything else. Hmm. Alright. See if you can think about it. It's going to involve a couple quantifiers. Did you see which ones kind of need to be here? Which words of these can you pick out and notice like they should probably be a quantifier? Do we find any? I'm not saying the words for all, and I'm not saying the words there exist. There exists, but this sentence has some words, right, that could maybe translate into for all, or there are synonyms for there exists. Do we see? How about haza? If you have something, right, it's there, it exists. So that's a there exists. Where's the for all? There's also a for all. Which word does that translate from? Yeah, every non-empty list. So anyone, for every non-empty list, there exists a minimum. See how you can translate that? It's the same thing, same idea. Now we have mathematical symbols at our disposal. That's pretty nice. So let's see if we can go further than that. All right, so let's figure this out. What does it mean that every non-empty list of numbers has a minimum? So first of all, we need to be able to quantify over this list. Right? We need to be able to say like this is a list and it has indices. Like we need a name for that list. So we have to create a variable. Right? We have to introduce a variable that stands in for our list of numbers that could stand in for any other list. Right? So we need to create a variable, call it L, let's say, for every list L. Right? So this is where we started. Every non-empty list of numbers has a minimum. We want to use symbols, and so we need a name for L. Kind of like need to make it in math, declare it in math. So this is what that translates into. This is the next step on our journey. Okay. So like we start here. Every non-empty list of numbers has a minimum. We're trying to make this more precise and closer to math. So here is getting a little bit better. For all lists L, yeah, now I have a name for those lists. If L isn't empty, then there exists a minimum value in L. Okay? So now we're spelling it out. So there's my for all. We can easily translate that into a symbol. There's my there exists. We know which quantifier that becomes. And then also we have some remember our ands, ors, and nots? That wasn't our only list of Boolean expression. We could also have an if-then statement. Remember that there's an if-then statement in math? That was our implication, our arrow operation. Remember that one? So that's getting a lot closer. So if this is true, then we have this. So you can put a quantifier in the middle. That's okay. We're going to need that. Okay. And then we have to talk about what it means to be minimum, right? There exists a minimum value. Let's try and get that down further into math land. Right? So what does it mean for something to be the minimum of something else? To be the minimum of a list, for example. So we have to say what we have to describe it. Using math, what does it mean to be a minimum? Why is it the minimum? What are the properties that every minimum should have in a list? Well, it's got to be the smallest thing, right? So if you're the smallest thing, then everybody is bigger than or equal to you. Yeah? So you are less than or equal to everybody. For every other element in the list, the minimum is less than or equal to everybody else. You see where you can add another quantifier in there? For every other element in the list. I'm smaller, I beat it still. Okay? So yeah, it's less than or equal to every other number in the list. That's what it means to be the minimum. And that every, you can build on that. That's like, there's your for all again. So there's another for all hidden in there. So we're going to need a few more variables to talk about, like, where was the minimum, and like relate it to the other numbers in the list. So we're going to need to create some new variable names in our mathematical expression that talk about, like, what was the index of the minimum, what was the indices of all the other numbers in this list that we're trying to compare. But we can get there, right? So let's see. See if I can make mathematical symbols for everything. So here we go. For all lists L, that's an easy one. We can start with that. For every list L, there it is. That's our symbol. If this is true, if L isn't empty, then this is true, right? So if L isn't empty, how do we specify that in math? Well, it's a list in Python. Let's say we can ask for its size, right? If it's not empty, that means its length, right? Len of L. If len of L is greater than 0, then, right? So there's my implication. There's my if-then statement. If this is true, then I want to claim something. Then there exists a minimum value in L. Now I need to make this, okay? Then there exists a minimum value in L. And so we have a lot to talk about here, and so we need to do it like this. We need to say that it's less than or equal to, that minimum exists, and it's less than or equal to every other number in the list, right? And we can use indices again, just like we were using over here. We were talking about the indices of all the numbers to mean that it's sorted. We can talk about the index of the minimum and compare that index to every other index, right? That's right. We're trying to say right here, we need to fill it in with there exists a minimum value in L. Here's how I'll write it in math. I'll use indices. To say that there exists a minimum value in L, I'll say that there exists a minimum index, all right, such that for every other index I, L's value at that min index is less than or equal to L's value at those other indices I, because it's always smaller, right? Pick any other index. It's always smaller. That's what it means to be a minimum. So this is a very precise way of saying, all right, there's got to be somewhere in the list. That's what min index is saying. It's got to be somewhere in that list, such that for every other index, even including that one, it's still smaller than or it's still equal to itself, right? For every other index, the minimum, the thing at that minimum index, is less than or equal to everybody else. So we're quantifying over every other I that we could possibly look at in the list. That's what it means to be the minimum. You are smaller than everybody, right? So there exists a minimum. And this is what it means for it to be the minimum. It's smaller than everybody. So there's also a for all involved there. Are there any questions about how I'm reading that? So just for posterity's sake, here's the English definition, or the English translation of this precise math, which really does mean every non-empty list of numbers has a minimum, but this is how I kind of read this. So for all lists L, that's this part, if L's length is greater than 0, so that's implying that it's not empty, right? If that's true, then there is an index in L called min index, such that this is true about that min index. Every index I in L, min index is smaller. It wins in that game. It's the smallest thing. It's smaller than any other index, and so I'm looking at all of them at once. I'm quantifying over all of them and showing that, oh yeah, this one's smaller than all of them. So do you see how that's what you want to prove? That's what you have to prove to see if it was the minimum. That's what it means to be the minimum. So this is just a sentence. This is just a statement. This is just a proposition in math that you could either prove or disprove. It is a true statement, but this is just something you can now go and prove, and everybody understands what you mean. Right? That's the first step. Proving it is next. That's what we'll talk about next time. But are there any questions about how I did that translation? We went as slow as we could possibly go, but it still is a little bit complicated, I do have to admit. But this is very, very precise now. You kind of see how if you proved all this, if you were able to prove this, that would give you this. That is the equivalent statement in very precise math lingo. That every non-empty list of numbers has a minimum. That's pretty cool. Pretty powerful, I think. So that's where I want to stop. Next time, we're going to try and prove it. We're going to prove these statements, and one way to prove something is to write a program to do it, which is kind of cool. So that's where I want to stop for now. I'll have to keep you on the edge of your seats, I know, to think about that. But you do have an SAT. You have a big SAT this week, so hopefully you've been working diligently on that. So remember that it exists. And let me give you your next essay so that you're ready to do something when you're done. So this is a bit, definitely not a 1,000-word essay. Again, I wouldn't be mean like that. Let's do 750 words. And this is a pretty light topic, all right? So you do have to cite one thing. That's not Wikipedia. I've given you some example of things that you might want to say. But here's your prompt. Just go and find your favorite painting, all right? Go pick your favorite painting, or find one if you don't have one. But list to me in your essay your favorite painting that was made sometime before 1900, right? Sometime before Photoshop existed, yeah? Before computers. So go and pick your favorite painting that was made before 1900, or go find one. So like it could be from the Renaissance era, it could be like Impressionist stuff, whatever you like. And then assume that the artist who made that painting that you like so much was alive today, and they made it on a computer rather than on a canvas, right? Using today's technology. Like they used a tablet like I'm doing in class. They used Photoshop. They used like virtual brushes, but they still like did all their brush strokes. But now it's just a digital image that you can then print and hang up. My question is, would that painting still seem as beautiful to you if it was made virtually like that? You like it so much, it was made on canvas back before 1900. Would you still like it if it was made virtually? Tell me why, or tell me why not, okay? And I just want you to give a good analysis, put on your critical thinking cap as you're supposed to do, right? So, yeah, pretty open-ended essay. Just write an essay of at least 750 words about that. And I want you to cite at least one work, please, in this essay. Here are some resources if you're having trouble searching for things. But are there any questions about that? Pretty lighthearted. But you tell me, would a artificially created painting be just as beautiful as the real thing to you? Why or why not? All right. So this has to do with digital art, because that's what this person would have made, right? If they were doing it today virtually, we call it digital art, right? So here are two people that I follow on Instagram of completely different ends of the realism spectrum. Here's hopefully these links still work. Here's somebody who does a lot of cartoony styles that I like, and then here's a person that does more realism stuff that I like. Will it load? We'll see. So here's somebody, and I love her cute drawings. I follow her, and so you can look at those. So that's one thing that you have the capability of doing if you're unfamiliar with digital art. And then here's this other guy. It's okay, he's done more, still futuristic, but more realistic kind of artwork, right? You can even get impressionistic style stuff still with digital art these days with your virtual brushes. But those are both ends of the spectrum. You can still create the same painting for sure. You tell me if you'd still like it. Okay? That's my question for you. I think that's everything I wanted to say. Any ideas about that? So this will be due in week 14, so another 2 weeks to do. Okay? So go off and find a painting if you don't have one in mind. But I think that's everything I want to say. So if there are no questions, that's all I got for you today.